So we'll start it out as a simple idea. This idea that we could have vectors that could add together. And we've talked about vectors already being like these things that represent magnitude, units, direction, like all that sort of stuff. We even talked about walking up and down the hallway. So we'll start off simple and be one-dimensional, then we'll branch out to 2 dimensions, okay? So like build it slow. So I have this system of, that's what they call them. They call them a system of vectors. So if I have a system of vectors that are vectors A, B, and C, I'd like to say that if I have A and I want to add vector A to vector B, I'm not using any like fancy notation or anything. I'm just calling them vector A, B, and C. If I have 2 vectors and they add up to become another vector, that other vector is given a name. The name is a resultant. And it's exactly what it sounds like. It's the result of adding other stuff together. It's the resultant. That's the name of the sum of vectors. And just like any vector scenario, I should have a reference frame. So that doesn't go away. In fact, it's even more important. More important than ever. North, south, east, and west. Make this be like an overhead view scenario. Sorry, I just realized somebody walked off with my ruler, so I had to grab myself a ruler. And we could say that we have vector A as a given. We'll say it's 5.0 meters to the east. Vector B is another given, 10.0 meters also to the east. Now we've defined east as being positive, and so graphically we can just draw this. We could say, okay, I want to add up these vectors. Typically, stylistically, there's always these little style things. People will say they want to have the resultant on the left-hand side of the equal sign. C equals A plus B. And we could write this out just algebraically. We could say, all right, well, A is 5.0 meters. Notice it's positive because we declared positive to be east. Plus 10.0 meters. And that one's positive as well. And I know the answer is what? It's not a trick. 15. 15.0 meters. And I could even say, look, it's to the east. Okay? So like I said, I'm not trying to be condescending. I'm just starting off real simple. But if we start off real simple, we should be able to draw a simple diagram. And so I want to say, how would I draw this graphically? Well, I'm not worried too much about scale, but I'll be kind of rough about it. This is going to be my vector A. And well, how would you add on vector B? There's actually this catchphrase that people use. It's called tip to tail, like a nice alliterated catchphrase, tip to tail vector addition. And it's just a quick way to remember that every time you add vectors, they get added up. So that it's almost like they snap together. And I think about like, Lego, the children's toy. There's like innie pieces and outie pieces, and they can only snap together a certain way. When you add vectors, they can only snap together as tip to tail. I'll show you what I mean by that. So I got this little cross to show where A started, a little arrow where it ends. I would draw another cross here where vector B starts and where vector B ends. And I would say, behold, I have added up vector A and vector B tip to tail. They snap together, like those Lego pieces, The tip and the tail are joiners, if you like, okay? And we can throw in some numbers. 5.0 meters, 10.0 meters. And really this is like, let's say illustration, but it's a vector diagram. It's a schematic of that thing that we just did. But how would I draw the resultant? Well, in one dimension it's kind of annoying because if they all just stack on top of each other, then you have to do a little bit of just an offset. And I would say vector A plus vector B sums up to give vector C. But I think visually it makes sense. Now, I try to be in the habit of making my resultants be double thick, so everybody can see which ones are my resultants. And if you want to be in that habit too, maybe you can color code, use different colors, or maybe you'll just remember. But honestly, whether it's color coding or double thick, it helps you to remember which one's the resultant. Okay, so in this case, the resultant's maybe a little bit on the obvious side, but I've made it double thick anyway just to make sure that's really clear. And it's 15.0 meters. Now I don't have to tack on east really, because the fact that I have a drawing and a reference frame already in frame tells you that it's east. Okay, that's the easiest thing. I can say, therefore, the resultant.
Excuse me, interruption. Would all link leaders leave the cafeteria right now? That is all link leaders to the cafeteria. Thank you.
All right. Yep. And then for the next one, I'm going to take a look at this other vector system called XYZ. Sorry, I can see people are still writing some things down there. Vector XYZ. Another nice, simple system, and we'll keep it one-dimensional. We'll keep the same reference frame.
Sad.
Yeah, this is XYZ. It's not sad. Sad's later.
That's pretty sad.
Okay, and if I have a system like this, maybe I'll start off strong from the beginning. Z is equal to X plus Y. And I might have the givens. X is equal to, and really if we're using proper variables, we might end up talking about displacement 1 and displacement 2 and displacement 3. I'm just keeping it simple here. 4.0 meters east, vector Y. 12.0 meters, this time to the west. Yeah. Hope everything goes well. Bye. Positive 4.0 meters, negative 12.0 meters. And then if I was going to sub in my values, I'd say, okay, well, z is equal to x plus y. Well, in mathematical speak, that means that I've got 4.0 meters plus 12.0 meters, or I could say minus 12.0 meters. And of course, in math, I say that's what? Negative 8. Negative 8.0 meters. Or I could say 8.0 meters west. But we got to be able to vector diagram this one out. So again, in a not terribly scaled way, I could say, all right, my first vector, vector x, goes over like this. 4.0 meters. And then remember, because we're in one dimension, you can't like draw vectors on top of each other very easily, so we just offset them a little bit, and we kind of just agreed to be okay with that. Kind of makes me think a little bit of a number line. Maybe. Vector y, 12.0 meters. And again, I'm not going to throw in the negative sign because I've already dealt with it directionally with the actual schematic. But then when it comes to drawing the resultant is from the beginning of the first one to the end of the last one. Because that's what I've got in my equation. It's the sum of them, right? And that's what it means to be a sum. So from the beginning of the first one to the end of the last one, from the tip to the tail of the whole system, that would be my z vector. .0 meters. And I can see that it's to the west visually. In the math, I could see that it was negative. They support each other, right? They're complementary ways of talking about things. And I can make a statement. I can say, therefore, the resultant is 8.0 meters west. Great. So some of this is just like visuals for stuff that we've talked about already. Some of it's stuff that we've got visuals that have been similar already for. I want to keep the same reference frame again. This time we want to go two-dimensional. So north, south, east, west. Make north be positive and east be positive, south be negative, west be negative. And we'll come up with a SAD vector system. So vector S is going to be 7.0 kilometers to the east. Vector A is going to be 6.0 kilometers to the north. Keep in mind that east and north are at right angles to each other, so this is definitely two-dimensional now. It's not one-dimensional or collinear, some people will say. That's an S. The vector hat over top of it. 7.0 kilometers, 6.0 kilometers. And there's going to be people that say, oh, well, the vector equation must be S plus A equals D. Let's add those up. It's 13, no problem. No, it's not 13, and it's a slightly bigger problem. Not a lot of a bigger problem, but a slightly bigger problem. Because when I go to do the vector diagram, I'm going to go to vector diagram first this time, not math first this time. I don't want to start with algebra this time. I want to draw the picture this time, just to make sure I've got this. What I'm saying is that the S vector goes like this. S, 7.0 kilometers. Where does the A vector go? Everybody point with their fingers. Yep, that way, right? So tip to tail addition is easier to show in 2 dimensions because nothing's got to be offset. You can actually connect them. You can properly snap them together in 2D. And you can imagine you can properly snap them together in 3D, but we're not going to go 3-dimensional with this course. We're keeping everything to 2 dimensions. 2 dimensions is enough, okay? So I could say A is equal to 6.0 kilometers, and that one's to the north. And so the answer really obviously becomes not 13. Agreed? It is not 13. In fact, I'm going to have to be I heard it. What is it? Pythagorean theorem. And not just Pythagorean theorem. You notice that in the past, we had vectors that had a direction west. Not just Pythagorean theorem, SOHCAHTOA. Oh man, got to deal with directions too, right? So we got to pile it all together. It's all good. So if this is my D vector here, when I go to actually solve this thing, this vector equation doesn't tell me to add 7 plus 6 is 13. It tells me the order that I snapped my vectors together in tip to tail order. So let's just be clear about that. This is telling me how to snap them together in 2D. Now I got to step back and say, well, actually, can everybody do that? I feel like this is one of those things where you push your glasses up on the bridge of your nose and say, well, actually, you know what I mean? Cartoon-wise, D squared is equal to S squared plus A squared. And we sub in our values, 7.0 kilometers squared plus 6.0 kilometers squared. And I feel like I just want to do it all in one go. Can I just square root both sides? Yeah? I'm doing it in red to match the hypotenuse of my triangle. I'm trying to be color-codey when I remember. What's the magnitude of D? Somebody with a calculator. I think it starts with a 9. Fire your hand up when you got it. I want to see who the quickest draw in the West is. You didn't put your hand up.
Oh, shoot.
What'd you get?
9.2.
Give me 4 decimal places.
Oh, 9.2195.
2195, all right. You know, we always want to hold on to a bunch of extra decimal places. 2 to 3 is a good rule of thumb. Kilometers. And he's right, we should round it off to 2 sig figs based on the givens, 9.2 kilometers. But we're not done yet. We got to find ourselves this here theta value. What do you like, sine, cos, or tan ratio? What's going to be the most reliable here? Tan, because we didn't round those guys yet, right? So tan's going to be our best friend. So tan theta, and I'm not going to use op and adj. I'm going to use A and S. because that's the vectors that I've named here. Theta is tan inverse of A over S, 6.0 kilometers. 7.0 kilometers. Somebody help me out. What's theta? Quickest draw in the room. Vigilantly waiting for the answer. Tan inverse of 6 over 7. Yeah? 7086? I gotta pause because I gotta double check.
Are you in the right format?
I have a funny feeling you might be in radians. Yeah, I think so. 40.601. But that's okay. That can still be a teachable moment. We want to remember that we want to be in degrees. I'm not quite sure where that number came from. If you got that number, you might have been in the wrong mode, radians or something. Were you in radians? All right, confirmed it was radians. That's okay. That was a quick draw, but a misfire. Closer to target next time. But then if we're going to do a therefore, we could say therefore because we don't have any real story here, we're just going to call it the resultant. Therefore, the resultant is 9.2 kilometers, open bracket, east, 41 degrees north. Now, if you constructed your triangle differently, or if you're really committed to using north as the first one, for example, you might have said north. How many degrees east? 49? All right, so that's kind of the basics for adding up vectors in 1 and 2